Welcome to chapter 4. So today we're going to talk about, in chapter 4, we start talking about the concept of energy balance of closed systems. Now, close is kind of important here because as opposed to open, close means that everything stays within the confines of a boundary and nothing crosses it but work and heat. So if I was going to draw, let me define what closed is. So this is a control volume. Should have drew it as a dotted line, but actually I'll just say go ahead, control volume. So it can have some depth to it. Doesn't have to be two dimensions. Now inside here, this is closed, which means that if there's, for example, typically inside of what we're characterizing in here is a gas or a liquid, and for chapter 4 we characterize both. It could be a liquid, a single phase liquid. Could be a liquid that's boiling. It could be a gas that's going from, that's rising or lowering in temperature. But the mass that stays in here remains in here. So I would just say the mass in here is constant. So let me see if I can just put C-O-N-S-T for constant. And the only thing that crosses the boundaries would be, for example, in and out would be heat, or it would be, let me see, so we can have heat crossing the boundary, and the other only area of interest crossing the boundary would be work. Go ahead, so it would be, thought I selected the color here. Alright, here we go. So there could be work coming in or work coming out. But mass will not come and go out of this volume. That's the only difference between the chapter 4 and chapter 5 when we start dealing with open systems. Now, I mean, don't get too caught up on the differences. Whenever you see mass coming in, like a flow of something coming in and coming out, that becomes an open system. And we'll need chapter 5 to study those. But just think of a box with gas inside, or a cylinder with a piston that doesn't allow the gas to escape, or the saturated liquid. This is what we talk about closed systems. Okay, so now there's an important concept with closed systems, and that's called moving boundaries that we're going to talk about. So a closed system, a moving boundary. So a closed system doesn't have to just be a rigid tank. It could be it could be moving, going up or going down, increasing in volume, decreasing in volume, as long as the mass stays constant inside. So let me go ahead and, if you remember, I'm going to go ahead and draw a pressure versus volume diagram. Now we've done this in class, and we actually had a quiz on this. So we'll put pressure on the vertical axis, volume on the x-axis, and let's go from a state or a point 1 or to an arbitrary point 2. So here we start at state 1. We are at high pressure, relatively speaking, to 2. 1 is higher pressure and smaller volume. And then let's just assume we go in this direction to point 2. And now point 2 is associated with a lower pressure and a larger volume. So it'd be kind of the equivalent of having a piston that's under pressure and then just expanding it and let it relieve. And that's exactly what we're doing. So at the bottom here, I'm going to draw what that looks like here. So I'm going to go ahead and draw I'll explain what I'm drawing here. So here would be V1, and this would be V2. That would leave us here. So imagine a piston chamber, and we had a piston in here that was at this location, arbitrary location, and we're going to move it to this location at some time in the future. So we know that there is, let's go ahead and draw a different color. These little arrows represent the pressure along the surface of this piston. And we know that pressure, so that's the pressure, and we're going to say that, let's see if we go to another color. We're going to sweep across an area, so just say we end up here, but sometime in the future we were over here. This area here is the piston sweep that we're going to call D volume, dV. So as the piston moves to the right, it sweeps across an area, so some arbitrary stop point here. It sweeps across an area that we call dV, which is a little area, an infinitesimal area. We assume that the piston just barely moves. And the minimum and maximum points are still V1 and V2. So that would be V1 would be at its lowest, the piston's lowest volume. And again, this is the rigid, this is all rigid here. Maybe I should just left it in green. So the volume is, when it goes to swings to V1, it's at its minimum. When it swings all the way to V2, it's at its maximum. So if we wanted to find with the work is associated, so the pressure across a distance will give you work, and so the boundary work is equal to the integral from 1 to 2 P dV, pressure times volume. Remember, the area under the curve of a pressure times versus volume curve gives you work. So this area here, this total area, would be from 1 to 2 would be the total work, the total boundary work. And we're just saying pressure times a small volume change is equal to the integral of that is equal to the boundary work. And how do we characterize area? Well, area, which is A, is equal to the integral from 1 to 2 dA. So this would be the total area, would be integrating from 1 to 2, or from 2 to 1, would be the whole area that we're applying the pressure across. And so therefore we replace, so that would be the area. Of course, a force over an area is a pressure, and that's how we substitute P dV. And so so we have that, and now let's assume that let's go ahead and start a new page. Okay, let's assume that we have, all right. So again, we start off with this would be volume, and this would be pressure. And let's say that we have, we start at 1 here. Again, this is state 1. And now let's assume that we go to state 2 sometime in the future over here. Now we have a certain way of getting there. Just imagine this is the path to get from 1 to 2. It's up here, goes up like that and comes down. Okay, we're going to call that path A. Now let's assume that we go from 1 to 2, we take a different path, maybe a more linear, direct path. We're still going from 1 to 2. That we'll call path B. And then finally, let's just say there's a different way to get from 1 to 2, and it's this path, which we'll call C. Okay, so work is path specific. Let me write that out. Work and heat are path dependent properties. So that means that to define the work associated, so let's assume we know that the area under the curves here are work. So that would be going the area from 1 to 2, but it's dependent on the path we take, right? So this would be V1 and V2. Look at the area under the curve C. Isn't that much smaller than the area under the curve A? It's much larger, right? So it's the work, which is the area under each individual curve, the work is different, and it's basically path dependent. I'll explain later the difference between path dependent properties or path dependent attributes like work and heat, and then things that are not path dependent like pressure. Okay, so now let's just assume that the work associated with A is 10 kilojoules. The work associated with B is equal to 8 kilojoules. And the work associated with path C is equal to 5 kilojoules. So depending on the path is which work is the amount of work it's going to take to go through that path. So now the area under these process curves on the PV diagram represent boundary work. So all this represents boundary work. So maybe a different color so we don't get confused here. This all represents boundary which we call WB. If you remember from the previous slide, that's the boundary work here. The boundary is basically, if you could imagine, let me go ahead and continue sweeping this area here. This cylinder is defined by the purple, the volume of the cylinder is defined by this purple line. So right here, at this position, it is that, and then it'll expand all the way out here, so this volume will stretch and will shrink. We'll stretch to a maximum at V2 and we'll shrink to a minimum at V1 and everywhere in between. So this boundary is always stretching and shrinking as the piston oscillates. So it's a moving boundary. And this is what we call boundary work. Going back to that picture, it's basically the work associated with this piston here. Because work is a pressure over a volume, or a force times a distance. Okay. Now if we were to go ahead and do a cyclic process, in other words, if we go back to, if we looked at volume on the X and pressure on the Y axis, and we went ahead and said, okay, so we're going to go again from 1 to 2, it could be we take this path to get from 1 to 2. This would be A, and then to come back, just say this is a cyclic process. We're going to go from 1 to 2, and then we want to go back from 2 to 1. So from 2 to 1, we may choose to go this way. And I believe one of the sections had a quiz on this too. Turns out that this area, so this would be the area under curve 1 plus the area under curve 2, or minus the area under curve 2 because we're going backwards. So this area here, go ahead and, so the area under curve 1 minus the area under curve 2, so let's see if we can say W A minus WB. that would represent this here, this area. And that is what we call the net, the work net. So it would be W net is equal to the area under A minus the area under B. And I didn't write B here. This should be a B. Okay, for path B. So that's the net work. Okay, so just keep that in mind. So remember, we need boundary movement in a closed system in order to have boundary work. So as an example, let's go ahead and do example 4.1 in your book. So in example 4.1, we have a situation where we have a rigid tank. And it starts off temperature, we're going to say temperature starts off at 150 degrees Celsius. And the pressure is 500 kPa. And then sometime in the future, once we remove heat from this tank, so let's assume that some heat is removed from the tank and that's coming out. Therefore, the temperature in here drops to 65 and the pressure will drop as well to 400 kilopascal. So now find the boundary work. Okay, well, right off the bat, this is a rigid tank, so the volume, if we consider this state 1 and this state 2, then the volume at 1 is equal to the volume at 2 because it's a rigid tank, and so there isn't a oscillating piston or anything, so the volume remains constant. So therefore, dV is equal to 0. And if dV is equal to 0, we have our integral equation that says that from the integral from 1 to 2 is pressure dV. And if this is equal to 0, then the boundary work is equal to 0. So the boundary work here is equal to 0, basically. If there's no moving boundary, then there is no work. Okay. Now, I think I'm going to have to create a new sheet again. Okay. All right. So then we have an example 4.2 in your book. Well, actually, example 4.2 is in English units. We don't really do English units. I wouldn't test you on it. So let's just skip that one. All right. So let me go ahead and wonder if I can undo this. And let's just get to the next subject. One more. Okay. So if we have so we're going to talk about something called isothermal compression of so it's the isothermal compression of an ideal gas. And isothermal means constant temperature. So if we do go ahead and write our gas law, it says that PV is equal to the mass times the gas constant times some temperature. But now temperature between state 1 and state 2 is constant. So that should be an M. So therefore, since mass is constant in a closed volume, and the gas constant is constant by definition, and the temperature is constant, therefore this is a PV, pressure times volume, is equal to a constant for an isothermal. This is only for isothermal, or an isothermal system, or specifically an isothermal compression. But it would be the same for expansion as well. And therefore, to write the boundary work is equal to the integral from 1 to 2 P dV, which now for P, so if we were going to go ahead and say that, this then tells us that P is equal to C over V. So if these are volumes, I'll put my little slash at the bottom to signify volume. So pressure is equal to a constant over volume. So therefore we go ahead and replace the pressure with C over V. We say dV. And we take the constant out of the integration. And we're very familiar with the integral of dV over V, which is equal to bring our constant times the natural log of V2 over V1. And then we can go ahead and replace our C and put back the PV. So we say PV natural log V2 over V1. And now, since pressure times volume is a constant, we know that we can say P1 V1 is equal to P2 V2, because after all it's just a constant. So for any arbitrary state, if we typically, right now we're going between state 1 and state 2, so P1 V1 is equal to P2 V2. So therefore this P and V can be any pair, any state. So we can say that this is also equal to P2 V2 natural log V2 over V1. And likewise, it's P1 V1 natural log. Right, so you get the point. P1 natural log. Let's see. Yeah, V2 over V1. Oops, went a little high on my hash mark, on my slash there. Okay. So that's what we get for a isothermal compression, and what we're looking for is boundary work. So boundary work, in a sense we already found it up here. Is here, and then we can just put in either for C we can put P1 V1 or P2 V2 depending on what information we're given. Now we have another case. It's called constant pressure. So for a constant pressure case, we're going to go ahead and create a new, give us plenty of space to write here. Alright, so now what do we do for a, alright, so for a constant pressure case, we have a situation, actually this was an example too of the book, and you can look at it even though it's in English units. We know the integral is P dV from 1 to 2, and since if we're dealing with constant pressure, then we say that P is equal to P1, which is equal to P2, which we're going to say is just P naught. And so therefore we put P naught here, and we take it, since it's a constant, we take it out of the integral. And we're just left with dV from 1 to 2, which is equal to PO V2 minus V1. And this is the boundary work for a constant pressure process. Constant pressure process. And okay. So now, if we're talking about energy, go change the color here. So energy balance, this was basically how I started the lecture. For a closed system, we say that the energy that goes into the system is equal to plus, excuse me, jumping ahead here. Hold on a second. So it's okay. So energy that comes in minus the energy that comes out is equal to the change of energy of the system. And the units would be in kilojoules. So this is the net energy transfer that we call on the left hand side here. And this is the change in internal energy back here on this side. So what do we mean by change of internal energy? So that would mean basically that would include the internal energy, the kinetic, and the potential energy. So it would include all those. And in rate form, we just put a little dot at the top. The rate of energy that comes in minus the rate of energy that comes out is equal to the rate of change of the energy of the system. Okay, this would be in rate form, and so the units would be in kilojoules per second, or kilowatts. Now, if we were going to go ahead and use a conventional form to write our energy balance of a closed system, we would go ahead and change the color, keep it interesting here. Sorry. If we would say that Q represents our net heat, so it would be Q in minus Q out. And then we would say that work represents the net work, which is work out minus work in. And I'll explain why these conventions change. But therefore, let me just say Q net in. This is because we have Q in at the beginning minus work net out with this term is equal to the change of energy of the system. But what you'll do is you'll usually just see this as Q minus W is equal to delta E. And this is basically the energy balance of a closed system. And now you have to keep in mind, though, these require you to use a sign convention. And so what we mean by that is you have to stick to the sign convention that tells you that. Let me go ahead and go back to my work. It tells me that work that leaves a system is considered positive, and work that enters a system is considered negative. So the way we usually refer to this is work. The system is producing work, and so we get a net positive, such as a turbine producing work once we once we have steam coming in and steam coming out. Though this is different here because this is a closed system, but I mean it's still the same sign convention for work. And then for heat, we do the opposite. We say, well, when heat leaves a system, we consider that negative. And when heat enters a system, we consider that positive. This is just our sign convention. You have to abide by that in order for this to work. And later you'll see in chapters, you can make this a little bit easier. And sometimes you can say, well, if you consider this Q in and Q out, and then of course work in and work out, then you can that's another way of, instead of putting positive negatives, you put you can, on both sides of the equation, you can put everything that comes into the system you put on the left hand side, everything that leaves the system you put on the right hand side. Okay. So let's go ahead and get into an example problem. And for this, since this example problem takes a little while, or takes a lot of space, might have multiple pages here, I'm going to create a new sheet. Alright, so this is example 4.5. We say a piston device contains 25 grams of saturated water vapor that is maintained at a constant pressure of 300 kilopascals. Let's start writing what we know here. I'm going to try to make this big. Right, so this is a cylinder, and this is a piston. A round piston inside of a round cylinder, and we say that we're given that there's 25 grams, so the mass in here is equal to 25 grams. We were given that what else have we been given? Constant pressure. We're saying that the pressure here is constant at 300 kilopascal. And therefore pressure P1 at state 1, pressure at state 2 is equal to 300 kilopascal. And inside here we have saturated vapor. So maybe I'll draw saturated water vapor. Saturated water vapor. Now it's important, water just means it's H2O in this case. So there's two things. It could be saturated vapor, it could be saturated liquid. Right now we know it's saturated vapor. A resistance heater within the cylinder is turned on, and the pressure of it passes a current of 0.2 amps for 5 minutes from a 120 volt source. So let's go ahead and draw a resistance heater. So there's a resistance heater. And we were given that there's a voltage potential here of 120 volts. That's our source. But the current that's passed in due to this voltage potential and the fact that there's a resistance heater here is equal to 0.2 amps. And the time lapse is equal to 5 minutes. So it's turned on for 5 minutes. At the same time, a heat loss of 3.7 kilojoules occurs. So a heat loss of 3.7 kilojoules. Let's see, where do we have the heat losing from here? Let's say heat loss, 3.7 kilojoules. Okay, so now we have to start solving problems here. It says A, we have to show that delta U plus the boundary work, sorry, so it's delta, this is not delta V, this is delta U, it's a capital though, plus the boundary work is equal to delta H. So if you remember from chapter 3, H is enthalpy. So we're going to go ahead and show you that the internal energy plus the boundary work gives us enthalpy. And so let's go ahead and do that. And then B, if we have time, we'll go ahead and it says B is to find the final temperature. So find T2. Alright, so let's start off with the energy balance. Energy in minus energy out is equal to the change of energy of the system. Now at this point we say that, well, then we go ahead and since the only thing that's happening here, we have there's basically this resistor represents work electric that's going into the cylinder, and this heat represents the heat that's being lost. So we're going to say that Q, so E in minus E out, we can replace that with the only thing that's the only energy coming in and leaving are work and heat. So we say Q minus W, we'll put that in green, is equal to, now we say it's the change of energy of the system. Well, what is the change of energy? It's the change of internal energy plus the change in kinetic energy plus the change in potential energy. And these we assume are zero. Why do we assume they're zero? Well, we're not given any velocities, and for these problems the piston, in order to have equilibrium, we have to move it slowly. So you have pretty much a non-existence velocity there, or one that's very close to zero. And then potential energy, we're not assuming large movements and large increases or heights, and we're not given any heights. So really there is no way of us determining the potential energy due to this cylinder going up and down. So so then basically we're saying that Q minus W is equal to delta U. Now let's go ahead and partition W. What is, remember we had, well, I'll just leave it in blue. We had Q minus W. So there's work, W is composed of work electric and work of the boundary. And so that is equal to change in U, which is U2 minus U1. And now for a constant, we can go ahead and determine what the boundary work is, because it's a constant pressure. So we know that the boundary work is equal to the pressure P naught times V2 minus V1. So we can replace that for the boundary work. And now we can go ahead and write that Q minus work electric minus PO V2 minus V1 is equal to U2 minus U1. Now, you remember what we said about P? P can be P naught is equal to P1, which is equal to P2. So therefore, we can just, when we multiply P naught times V2, we'll change the naught symbol into a 2 symbol. And when we multiply P naught times V1, then we change the naught symbol into a 1 symbol because all these pressures are equivalent. So again, when we go ahead and multiply by pressure, we get two terms here. And again, we're going to change the subindex there accordingly. And when we do that, we have that we can go ahead and if we group everything that's so we can go ahead and do what we just said and regroup, and we'll get something that looks like this. Q minus work electric is equal to, and we put everything on the right hand side. So this we're going to put on the right hand side of the equation and regroup with each in these subindex U2 and U1. We're going to get that U2 plus P2 V2 minus U1 plus P1 V1. And by definition, the internal energy plus pressure times volume is equal to H for each case. So this is just H2 and H1. So we have that Q minus W, work electric is equal to H2 minus H1. And that is basically equal to delta H. So that's what we have here. So in some respect, we prove this, or we show this, and that's what we were asked to show. Okay, so that satisfies A. For T2, how are we going to find T2? Well, it requires a little bit more work. All right, just a second. All right. So we have now for A. I'm sorry. So we needed to see what we can do with this work electric. Well, we know that work electric is equal to the voltage times the amperage times the change in time. So this is basically, as opposed to temperature, this is time. And the delta tells us the time lapse. So together it's just basically the time lapse. Alright, so what do we know here? We know that the voltage is 120 volts. We know that the current was given as 0.2 amps, and we were given the time lapse was equal to 5 minutes. Now we don't want to, we're going to have the answer, we're going to have to change it in order for consistency. We'll change it to seconds. So we'll convert it by multiplying, what do we say, in a minute equals, each minute is equal to 60 seconds, right? 60 seconds per minute is our conversion factor. And so therefore, this gives us that the work electric is equal to 7.2 kilojoules. You want to make sure you convert to seconds here because, I'm sorry, did I say this? I don't know why I wrote. This is not 600 seconds, this is 60 seconds. 60 seconds in a minute. All right. So again, 120 times 0.2 gives us the power in terms of watts or kilowatts, right? So that's why we need to convert this 5 minutes into seconds so that we can multiply kilowatt is a kilojoule per second, so that we can have our seconds cancel and get kilojoules. All right, so for state 1, So state one was when before we introduced the electric work, before we turned on the switch to the resistor for across 5 minutes. So for state one, we know that the pressure, well, since it's constant, 300 kilopascal, and we were given that the state is saturated vapor. So these are two independent properties that we need, and therefore if we go to the appendix, and since we're given pressure, we use table A5, which is our pressure table for saturated water. Then we get our enthalpy, and we say, well, enthalpy 1, enthalpy 1 is equal to, since it's saturated vapor, it's G at 300 kilopascal. Which is, from the table, is equal to 272.49 kilojoules per kilogram. Taken from table A5. And then we say that, well, again, using the first law, E in minus E out is equal to change of energy of the system. System being this piston with the saturated vapor inside of it initially. We say that work electric in minus Q out is equal to, well, what is our change of energy? We had determined that if you assume kinetic and potential energies are zero, and if you combine the boundary work with the internal energy change, then, if that was from our last example, then you can say that this is just equal to delta H. And delta H, delta capital H, is equal to the mass of the system times little delta H, which is H2 minus H1. And now if we went and substituted for our electric work, 7.2 kilojoules, for our heat loss, which is 3.7 kilojoules as given, this is equal to the mass, which was 25 grams, so we'll put it in terms of kilograms, times, well, we don't know what H2 is, that's where we're trying to find out in order to find the temperature, minus H1, which is 272.4.9. I think I put the decimal in the wrong place here. Let me fix that here. Sorry about that. Hope this doesn't get confusing here. The decimal's right there. Okay. Now we solve for H2. And H2 is equal to 2864.9 kilojoules per kilogram. Now, this is very interesting. So we had an increase. So H2 went up relative to H1, right? And that makes sense because what we did is we went ahead and put electric work inside, which basically ends up putting energy, and the energy that enters the piston effectively raises the heat. Even though we have Q out, we have more going in than we have coming out, right? We have 3.7 kilojoules coming out. We have 7.2 kilojoules from the electric work coming in. So we expect a temperature change, and when there's a temperature change, well, the enthalpy is also going to change. It's going to go up. And if we started with saturated, we had saturated vapor in here. Remember, we're teeter-tottering here between, if we put energy, one last bit of energy here, everything remains the same. If we leave the Q out the same, but if we add just a little bit extra energy, then we go into superheated, into the superheated world, and that's what we're doing. So we started at saturated water vapor, and we're obviously putting work in, and we're taking heat out, but it's less than the work we're putting in. So we're going to go into superheated vapor. So we are now at superheated vapor because we were right at the hairy edge anyway, and we just put a little bit of network coming in. We're at superheated vapor. That's table A6. So you go to your table A6, and you know that you know what P2 is. Doesn't change. It's 300 kilopascal. And you know H2, and that's all you need is two independent and intrinsic properties. It's 2864.9. And that is equal to, it turns out when we look up in the table, temperature is equal to 200 degrees Celsius.